So today we're going to talk about molecular orbital theory. This is the most complicated bonding theory we're going to talk about. In molecular orbital theory, which is often abbreviated MO, the orbitals are calculated for the entire molecule instead of for individual atoms. So even for a simple molecule, it's impossible to solve the Schrödinger equation that describes the orbitals. So what they do is they start with a trial function as an educated guess, and you put that in and see how it turns out, and then you modify that a little bit to see if you can get the energy lower. And so computers are used to calculate the energy and then optimize it for the lowest energy. And of course, we're trying to just describe what nature is already doing, and we can never do better than nature at minimizing the energy of an orbital. So one way to think about the molecular orbitals is to think of them as a linear combination of atomic orbitals. That's kind of a mouthful. That's abbreviated LCAO, linear combination atomic orbitals. This is a weighted linear sum of the valence atomic orbitals of the atoms in a molecule. It's the simplest trial function that works reasonably well. These linear combinations combine the valence atomic orbitals of all the atoms in a molecule. Not just the two atoms in a bond, but all the atoms in the molecule. That's why it's called molecular orbital theory. In valence bond theory, we're only looking at hybrid orbitals combining orbitals on a single atom, and those overlapping with possibly hybrid orbitals on another atom. So many of these linear combinations of atomic orbitals are delocalized. They are spread over the entire molecule, whereas the hybrid orbitals remain localized on a single atom. You're kind of grasping the difference in principle between these two methods. Valence bond theory, we're looking at localized orbitals. In molecular theory, we're putting orbitals over the entire molecule. So let's look at a very simple molecule, H2. Can't get much simpler than that. So the valence orbitals are 1s for each of these hydrogen atoms. And when we combine these two as a weighted sum, we're going to weight these equally. And one way to combine those gives us something like this. This is a bonding orbital because it's lower in energy than the two atomic orbitals that it was formed from. It's called a sigma orbital because of its shape. If you were to look at the end of this, this is sort of like a capsule shaped. If you looked at it end on, it would be a circle. So just like the sigma bonds we talked about, we use sigma to indicate the shape of this. The next molecular orbital is made by summing a 1s orbital with a positive phase and a 1s orbital with a negative phase. So basically it's like destructive interference. And when we do that, you could also think of this as subtracting rather than adding the orbitals. Then we get something that looks like this. There's a node in the middle, and one side has a positive phase and one side has a negative phase. This is higher in energy, and so we refer to it as an antibonding orbital because in order for these two atoms to bond, we want things that are going to lower the energy. If we're getting orbitals that increase in energy, that's fighting against bonding. So it's called an antibonding orbital. This is also a sigma orbital because if we look at the end, it's going to be spherical. So this is called sigma star because it's an antibonding orbital. Any questions yet? Yes?
So is constructive interference based on the bonding orbitals?
Yeah, constructive interference is what gives us the bonding orbitals. So they're reinforcing the electron density, and the antibonding is the destructive interference, where it's basically destroying the orbitals. It's separating them and making them higher in energy. So these are added or adding two in phase. These are subtracted or adding two that are in opposite phases. So we get this sigma, we call this a sigma 1s because it's formed from 1s orbitals. This one's sigma star 1s because it's also formed from 1s orbitals. Notice that we're doing with this with two orbitals. We start with two atomic orbitals, we end up with two molecular orbitals. So however many orbitals you throw in here, you're going to get the same number out. It's the same idea as with valence bond theory. This bonding orbital has increased electron density between the two nuclei. These dots here represent the nuclei. And the antibonding orbital has lowered electron density, in fact, a region of 0, a node between. And then we have density closer to each atom. So this is fighting against bonding, this is promoting bonding. Well, drawing all those pictures can get a little awkward. So we make diagrams. So we made orbital diagrams for individual atoms. Now we're going to make orbital diagrams with molecular orbitals. So these are called molecular orbital diagrams. So we do indicate energy here. Higher energy is up and lower energy is down. We're going to look at the two atomic orbitals that we're combining. So we have a 1s orbital on this hydrogen atom and a 1s orbital on that hydrogen atom. These electrons are going to end up pairing over here, so we'll put one with spin up and one with spin down. When we put these two together, we get a bonding orbital, which is lower in energy, and an antibonding orbital, which is higher in energy. Then each of these atoms is contributing one electron, and so we're going to fill up these molecular orbitals following the same ideas as we did with atomic orbitals. That the electrons are going to go into the lowest energy orbitals first. If there's degenerate orbitals, they'll fill those separately with parallel spins before they pair up. So we have two electrons, we'll put both of them in this bonding orbital. Any questions yet? We can kind of quantify how well this bond is going to be working using something called the bond order. And we're only going to be talking about diatomic molecules, just two atoms, because we just need to get the concept of molecular orbitals. We don't actually have to thoroughly understand it. So we're only looking at diatomic molecules. So the bond order is the number of electrons in bonding orbitals minus the number of electrons in the antibonding orbitals divided by 2. So basically it's an average, right? So for hydrogen, the bond order is 2 minus 0 divided by 2, come on pointer, which equals 1. So let's go back to that diagram and see where that comes from. So the bond order is going to be the number of electrons in bonding orbitals. So here's our bonding orbital. There's 2 electrons in there, right? So that's 2. And we're going to subtract the number of electrons in antibonding orbitals, which is 0. And then we're going to divide by 2. Because we're looking at bonding and antibonding. Bonding's positive, antibonding's negative, and we're going to divide by 2. And so that gives us a bond order of 1. Does that make sense? Makes sense to Chris because he's heard it before. This is weird stuff. If the bond order is positive, that means you have more electrons in the bonding orbitals, and a chemical bond will form because this results in a net lowering of the energy. The larger the bond order, the stronger the bond. If you get a negative bond order, the bond will not form, because that means that putting this combination together increases the energy of the system, and that's just not going to happen. Okay? So bond order positive, the bond will happen, and the larger the bond order, the stronger the bond is. A bond order of 0 also results in no bond because there's no benefit. So if we look at He2, helium doesn't form compounds, but we can pretend, right? Let's see what happens if we put 2 helium atoms together like we do with the hydrogen atoms. So helium also has a 1s orbital, so we have 2 1s orbitals. We combine these, we get a sigma and a sigma star, with the bonding and the antibonding orbitals. And then we now have 4 electrons to stick in here. So we put 2 in here, and then the other 2 go in there. When we calculate the bond order here, it's the number of electrons in bonding orbitals, that's 2, minus the number of electrons in antibonding orbitals, also 2, divided by 0, and that gives us, divided by 2. You can't divide anything by 0. It's Monday. 2 minus 2 divided by 2 is 0. So molecular orbital theory predicts that a helium-2 molecule does not exist, would not form, and it doesn't. There's no benefit in doing that. Any questions yet? What if we do an He2 plus? So this would be an ion. We're going to be looking at some just really weird looking molecules and ions here. Just bear with me. So He2 plus. So that's 2 helium atoms. Positive charge means we've lost 1 electron. So we've got this same molecular orbital diagram, but now we have a different number of electrons. So here's the helium atom with 2 electrons, and over here we're going to put an He plus ion with 1 electron. We're doing that because we're looking at this molecule, this ion, and it has a total of 3 electrons. And so we have to put them somewhere. So we'll put 2 on one and 1 on the other. Now when these combine, we're going to get 2 electrons in bonding orbitals and 1 in an antibonding orbital. So the bond order here, 2 in bonding orbitals minus 1 in an antibonding orbital, that quantity divided by 2, so this gives us 1/2. That's positive, and so we predict that He2 plus ion exists, and it does. Now, it's not something that you just run into all the time, but you can make it happen. Yes?
Do you just fill the bonding orbitals first?
Yes, you do fill the bonding orbitals first. So we draw the molecular orbital diagram. And then we look at, how many electrons do I have? I have 2 over here and 1 over there. I've got 3 electrons, and I'm going to put them in the molecular orbitals. And we're going to put them in the lowest energy orbitals first, and then go increasingly higher energy orbitals. Here we don't have any that are degenerate, but we'll get to that in a minute. If you have 2 or 3 orbitals that have the same energy, then just like with the p orbitals in regular quantum mechanics, you'll put 1 electron in each. So this is a summary. We approximate molecular orbitals as linear combinations of the atomic orbitals. The number of molecular orbitals will equal the number of atomic orbitals. So however many orbitals you put in there, you're going to have the same number. So it's a little bit like the valence bond diagrams where I told you, okay, so however many little squares you start with for the orbital diagram of that central atom, you need to end up with the same number of squares, right? Orbitals are conserved. When 2 atomic orbitals combine to form 2 molecular orbitals, one will be lower in energy and the other will be higher. One is reinforcing, so lowering in energy. The other is destructing or interfering with itself and will cause higher energy. When assigning electrons to those molecular orbitals, you fill the lowest energy ones first with up to 2 spin-paired electrons. We're going to follow Hund's rule, where we fill the orbitals of the same energy singly first, and then we pair them up. So in the hotel, this is the electrons taking their own beds before they start sharing in the same room. Stable bonds require a positive bond order, meaning you need more electrons in the stable bonding orbitals than you have in the antibonding orbitals. Okay, so let's use molecular orbital theory to predict the bond order in H2+. Is that bond stronger or weaker than the H2 bond? So we're going to draw a diagram. So here's our energy, and we're going to start with, we've got a hydrogen atom over here with a 1s orbital, and we've got a hydrogen atom over here with a 1s orbital. But this is H2+. So each hydrogen atom has 1 electron, right? But in this polyatomic ion, how many electrons are there? There's only 1. That's how we get the positive charge. So I have to take that electron away. It doesn't matter which side you put the ion on. So we're looking at a hydrogen atom and a hydrogen ion. These two 1s orbitals, when they overlap, will form 1 bonding orbital and 1 antibonding orbital. So this will be the sigma 1s, and this will be sigma star 1s. And we often do this dotted line thing so we can see. Okay, those 2 molecular orbitals came from these atomic orbitals. So this is atomic orbitals, and this is the molecular orbitals in the middle. Any questions yet? So to fill in the molecular orbitals, I need to look at, well, how many electrons do I have? Well, I only have 1. So I'm going to put that 1 electron in the lowest energy orbital, and I'm done. So they're asking us to predict the bond order. So you draw the molecular orbital diagram, and then the bond order equals the number of electrons in bonding orbitals, so that's 1, minus the number in antibonding orbitals, which is 0, divided by 2, so that equals 1/2, right? So this is the answer to the first question, or instruction, predict the bond order. And then it asks, is this bond stronger or weaker than the H2 bond? You got stronger and weaker. Anybody want to give a tiebreaker? Weaker. It's going to be weaker. Because what's going on with the H2 molecule? We've got another electron, right? The other electron is going to go here. The bond order in an H2 molecule is 1. They're both positive, they'll both form, but an H2 bond is stronger because the bond order is 1. So this is going to be weaker than H2, because the H2 bond order equals 1. Any questions? Okay, so we took care of period 1 in the periodic table. It's the first 2 elements, right? Now we're going to move on to period 2. So period 2, homonuclear diatomic molecules. That's a mouthful. Homonuclear, what that means is the same nucleus, diatomic, 2 atoms. So this is 2 atoms and they're the same element. 2 atoms of the same element. So here we have lithium, element number 3. just moving right along here. So here's a lithium atom, and here's a lithium atom. We're looking at the valence electrons, okay? We're looking at the valence electrons. So lithium has one valence electron. It's in the 2s orbital. 2s orbitals are going to combine and form bonding and anti-bonding orbitals very much like the 1s orbitals do. So this is a sigma 2s and this is sigma star 2s. Each of these atoms has one electron, and so when we put them into the molecular orbitals, they're going to both go into this bonding orbital. So the bond order for this molecule is 2 electrons in bonding orbitals minus 0 in non-bonding or anti-bonding divided by 2 is 1. So Li2 has a bond order of 1. It does exist in the gas phase. Yes?
I thought the only diatomic elements were the ones in the non-atomic.
Yes. You thought the only diatomic elements were those 7. We lied to you? Lithium 2 is not a common form of lithium. At regular temperatures and pressures, lithium is a solid, right? Whereas those 7 diatomic molecules or elements, those are their normal state at room temperature and atmospheric pressure. What this is showing, though, is that Li2 can exist. It exists in the gas phase. To get metals into the gas phase, it has to be at a very high temperature. Any other questions? Like I said, we're looking at some really weird molecules and ions. So, beryllium. Beryllium has 2 valence electrons. They're both in the 2s orbital. And we're combining these same 2s orbitals. We're going to get the sigma 2s and the sigma star 2s. But now when we fill the molecular orbitals, we've got 4 electrons. And so we put them in 1, 2, 3, 4. So we fill the lower energy orbitals first and then the higher energy orbitals. The bond order for this is 0 because you have an equal number in the bonding and the anti-bonding orbitals. And so 2 minus 2 is 0, divided by 2 is 0. So this is predicted to be unstable, and it is. When we get to boron, now we're bringing p orbitals into the mix. So we need to look at what happens when we create molecular orbitals from the p orbitals. So we can take the 2px and the 2px orbitals from both of these atoms and add them together. If we add them together so that the lobes that are overlapping are in phase, we get a bonding orbital. And if we add them together so that they're out of phase, we get an anti-bonding orbital. So this is like adding 2 p orbitals, and this is like subtracting 1 from the other. Putting 2 out of phase would be adding 1 and subtracting the other. So we get bonding and anti-bonding. These also are symmetrical around this nuclear axis, the internuclear axis, and so these are sigma. So this is sigma 2p and sigma star 2p. Does that make sense? There's 2 other p orbitals. So if we look at py for both of these, and we add these together, adding those together is going to look a little different because they're not going to overlap end to end. This has some commonality with valence bond theory when we were looking at the overlap of orbitals. Here, when we add these 2 orbitals together in phase, we're going to get a 2-lobed orbital where one side is negative, one side is positive. And if we add them out of phase, we're going to get something like this. So this increases electron density between the nuclei. This decreases electron density. This fights against bonding, and this promotes bonding. These are not symmetrical along the internuclear axis. And so these are called pi orbitals. pi orbital. So sigma, if you look down the end from nucleus to nucleus, it's a circle like a sigma. And when you overlap these side to side, this is a lot like forming those pi bonds in valence bond theory. We get this side to side overlap and we get something that looks like that. So this is called pi 2p and pi star 2p. Okay? There's one more pair of orbitals. This is pz and pz. So they're parallel to each other. When these are combined, we get a bonding orbital and an antibonding orbital. So this is the same shape as the one from the py. It's just oriented differently. So now we're looking at it from a different perspective. And so now it's even clearer to see. It kind of resembles the letter pi. So this is pi 2p and pi star 2p. Any questions? So just, to make things a little more complicated, the relative energy ordering for the molecular orbitals that we get by combining the 2p atomic orbitals is not the same for all molecules. It's actually determined using very complicated math and computers. It turns out that B2, C2, and N2, those next three elements, have a different order than oxygen, fluorine, and neon diatomic molecules. So the typical order is that the sigma is the lowest and the sigma star is the highest. Pi is in the middle and pi star is above that. Okay, so here we have what happens with boron, carbon, and nitrogen, and this is oxygen, fluorine, and neon. So this is the expected order. So let's look at this one first. Here you have your s orbitals, and they're just doing their thing. The s orbitals are lower in energy than the p orbitals, and so both of these molecular orbitals are going to be lower in energy than any of the p molecular orbitals. When we combine the p orbitals, we're going to get two sigma orbitals. One is bonding, one is antibonding, and we're going to get a total of 4 pi orbitals, 2 bonding and 2 antibonding. Because we're starting with 6 boxes, 3 boxes here and 3 boxes here, so we need to end up with 6 boxes in the middle. So this is very nice and symmetrical. The sigmas are on the outside and the pi's are in the middle, right? And the bonding is always lower in energy than the antibonding. This is what we think of as the expected or the normal energy ordering. Boron, carbon, and nitrogen don't follow that pattern. And one way we can remember which ones we have to watch out for is this phrase, be careful now. B for boron, C for carbon, N for nitrogen. For boron, carbon, and nitrogen, be careful now, the order is different. So what's happened here is the sigma star and the pi star, those are the same, but the sigma and the pi, these bonding orbitals, have switched places. See that? Here pi is lower than sigma, here sigma is lower than pi. So we're just switching the order of those two. Any questions? Why does it do that? It has to do with mixing of the s and the p orbitals. So there's more mixing for boron, carbon, and nitrogen, and so that causes the order here to switch. This slide is just for those of you that are curious. Why would that happen? If you're not curious, forget that happened. Okay, so here we're looking at molecular orbital diagrams for B2, C2, N2, O2, F2, and Ne2. Now, some of these are molecules that we're familiar with, right? Nitrogen, oxygen, fluorine, we know that those are diatomic elements, right? So we expect to see molecules like that. Ne2, do we think that might be a good thing? No, it's a noble gas. Why would it do that? And we haven't seen boron and carbon do this diatomic molecule business either. So here we have the different diagrams. The order is different for these first three because be careful now. Their order is different. The sigma and the pi order is different. So for these guys, the pi bonding orbitals are lower than the sigma. The antibonding orbitals keep the same order. So for B2, boron has 3 electrons, right? 3 valence electrons. So when we've got 2 of those together, we have a total of 6 electrons to stick in here. 1, 2, 3, 4, 5, 6. So we can calculate the bond order. We're looking at the number of electrons in the bonding orbitals. So 1, 2, 3, 4, minus the electrons in the antibonding orbitals. So 4 minus 2 is 2, divided by 2 is 1. So the bond order here is 1. So this is predicted to exist. And here is also the bond energy and the bond length, and we'll look at those in a minute. Carbon 2 has 2 more electrons, and so those are going to go here into these pi bonding orbitals. This has a bond order of 2. Nitrogen, we're adding 2 more electrons. Those are going to go into this sigma orbital. And the bond order here is 3. Now, oxygen, fluorine, and neon have the expected order for the sigma and the pi. So the sigma bonding orbital here, sigma 2p, is lower in energy than the pi 2p. So oxygen, each oxygen has 6 valence electrons, so we have a total of 12. So we've got 2, 4, 6, 8, 10, 11, 12. Calculate the bond order. This is a bond order of 2. Fluorine, we're adding 2 more electrons. Those are going to have to pair up here in this antibonding orbital. We have more electrons in the antibonding orbitals, and so now the bond order is going back down. This is 2. And we get to neon, and neon has an equal number of electrons in bonding and antibonding orbitals, and so the bond order comes out to be 0, which is kind of what we expected, that this would not actually exist, wouldn't form. When we look at the bond energies, remember, larger bond energy means it's a stronger bond. And bond length, generally a shorter bond is a stronger bond. And so we see there's a pattern here. As bond order increases, bond energy increases, and the bond length decreases. So nitrogen is at a maximum here, and then it starts going down again, and we see that the bond energy is decreasing and the bond length is increasing. Any questions? So molecular orbital theory explains something that valence bond theory cannot. We know by experiment, and I'm going to show you in just a minute a YouTube video, that oxygen is paramagnetic. Remember, paramagnetic is when you have at least one unpaired electron. Diamagnetic, di meaning 2, is when the electrons all come 2 by 2, like Noah's Ark, and it's not responsive to a magnetic field. If we go back here and look at oxygen, oxygen has 2 unpaired electrons in the molecular orbital diagram. I think we'll watch the long version. So that's liquid oxygen.
So we're going to take this oxygen gas, pass it through this copper coil that's immersed in liquid nitrogen. The liquid nitrogen will condense the oxygen into liquid oxygen, which will collect here in this pre-cooled orbital. We will then take the liquid nitrogen and pour it between the poles of this magnet. We'll pass the oxygen also, pour it through the poles of the magnet. Then we're going to see if there's any difference between liquid nitrogen and liquid oxygen.
Sorry, that's not oxygen, it's nitrogen. So by passing the oxygen gas through that, you make it really, really cold and condense it into a liquid. Liquid oxygen. See how cold that tube is? This is a really big magnet. He's pouring liquid nitrogen, and just kind of like you would expect with a liquid, it's just running right through. And here's the oxygen. What? It's stuck between the magnets. Because it's paramagnetic, liquid oxygen will stick there. The liquid nitrogen doesn't. That's cool. Super cool. Crazy cold, actually. This vapory stuff looking here, that's the, you see the cold of from the liquid oxygen, and as the air hits that, it condenses the water. So it's not actually steam or anything, it's just like condensed air. And as it warms up, it's just going back to a gas, and then it's going. Oh, what's that? It's a really, really strong magnet. Okay, so any questions about that? Let's try it. Yeah, that'd be fun. That would be fun. Lost my pencil. So we just saw demonstration that oxygen is paramagnetic. It must have unpaired electrons. Right? If we look at the Lewis model of oxygen, do you see any unpaired electrons? Here, Lewis structure. They look all paired up, don't they? Here's the valence bond model for O2. So here we have a sigma bond, and we have a pi bond, and we've got lone pairs, and everything's paired up, right? So this is pointing out a deficiency in both the Lewis model and the valence bond model, which is why, one of the reasons why we looked for a more descriptive, a more involved model. So molecular orbital theory can explain some of these things that valence bond theory cannot. So let's draw a molecular orbital energy diagram and determine the bond order for the N2 plus ion. Do we expect this bond to be stronger or weaker than the N2 molecule? And is this ion diamagnetic or paramagnetic? Okay, so we've got, not that one. We have energy increasing. We've got two, we're going to start with two nitrogens. So we'll put nitrogen over here. And what are the orbitals, the valence orbitals for nitrogen? 2s and 2p. So I'm going to do this carefully so that I have enough room to do everything. Put this one down here. So we got 2s and 2p. And then over here we have another nitrogen atom with 2s and 2p. We're going to have N2 plus, so one of these has to be N plus. So nitrogen has 5 valence electrons, right? 1, 2, 3, 4, 5. The N plus would have 4 valence electrons. 1, 2, 3, 4. Now we have to draw those crazy molecular orbitals. Well, the S one's not too bad. It forms an antibonding and a bonding. So this is sigma 2s, and this is sigma star 2s. And so those are coming from these s orbitals. And then the p's get a little more complicated. The sigma star 2p orbital is going to be highest. And then we're going to have the pi star 2p orbital. And then it's those two in the middle there that we have to think about the order. Nitrogen, be careful now, is the unexpected order. It's not the expected order.
Isn't the lowest one energy supposed to be applied to us?
No, from the S we get sigma and sigma star. S orbitals can only make, I've got 2 more things to put in here. Yeah. So I need a sigma and a pi bonding from these p orbitals. So far I've only drawn the antibonding orbitals. Normally this is really nice and symmetrical. Sigma's on the top and sigma's on the bottom, but this is the weird one. Be careful now. And so the sigma, the bonding orbital is here, and the pi bonding orbital is lower in energy. These are definitely challenging to draw. And note to self, I should probably put all of this writing over here and give myself this whole side, and that would make drawing these things a lot easier. The good news is, on an exam, I'll give you the diagram and just ask you questions about it. You'd have to put electrons in, answer things like, is it paramagnetic, diamagnetic, what's the bonding order? But I'm not going to make you draw these. For one thing, I don't want to have to look at them and evaluate them, because this sounds painful. There's a reason I'm not an English teacher. I like things where there's right answers and wrong answers. So now that I've got these molecular orbitals, I'm going to look at the total number of electrons I've got. I've got 5 over here and 4 over here, and I think 5 plus 4 is 9. So I'm going to put the 9 electrons in here. 1, 2, 3, 4. 5, 6, then they're going to have to pair up, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Following the same rules as we did when we were filling regular atomic orbitals. No more than 2 in a box, they have to be spin paired, and if you can, you put them separately. Low energy to high energy. So what's the bond order? Well, the bond order is the number of electrons in bonding orbitals. So what are the bonding orbitals? Well, this is a bonding orbital, and this is bonding, and this is bonding. So 1, 2, 3, 4, 5, 6, 7. 7 electrons in bonding orbitals. And how many in antibonding? 2. So that's divided by 2. 7 minus 2 is 5, so that's 5 halves, or 2.5. So that's the bond order for the N2 plus ion. For the N2 molecule, the bond order was 3. It's on a previous slide if you don't believe me. So, which is stronger, the bond in the N2 or the N2 plus? The N2, the one with the larger bond order, is stronger. So, the N2 plus bond is predicted to be weaker than N2. Okay? Then the next question, is this ion diamagnetic or paramagnetic? Di means 2, 2 by 2, like Noah's Ark, everything's paired up. Are all these electrons paired? No. One is not, so paramagnetic. Okay? Any questions? What about heteronuclear diatomic molecules in the second period? So 2 different atoms. So here's one of my favorite molecules. No. Can I go to the flea market with my friend even though I haven't washed the dishes like you told me 3 days ago? No. That happened. 13-year-old girls. Oh my goodness. So here we have a nitrogen and an oxygen atom. So here are the atomic orbitals for nitrogen, the atomic orbitals for oxygen. Oxygen's more electronegative. Its orbitals are a little lower in energy. Now that's not something that I would expect you to know. I'm just telling you. So its orbitals are a little lower in energy than the nitrogen orbitals. So then when we combine these, don't know how I did that, but I need the green arrow. Sheesh. There we go. Green arrow. I don't know why I like the green arrow. I do. It matches over here. Combining orbitals that are different in energy, then the molecular orbitals are going to look a little bit different. The lower energy atomic orbital contributes more to the bonding orbital, and the higher energy atomic orbital contributes more to the antibonding. And we really see that how it's skewed here, that this is closer to this one and this is closer to that one. But then we've got 5 valence electrons for nitrogen, 6 for oxygen, and so we stick them in here, 2, 4, 6, 8, 10, 11. So we could calculate the bond order, we could say that this is paramagnetic. Any questions? Some really funny things happen with fluorine. Remember, fluorine is the most electronegative element. So if we try to look at HF, a hydrogen atom and a fluorine atom, fluorine is so electronegative that all of its orbitals are lower in energy than hydrogen's 1 atomic orbital. This is really weird. So we're not even looking at the s orbitals when we combine and make molecular orbitals here. We've got the s overlapping with p orbitals, and so we're going to get 4 orbitals here, and this is going to have a sorry, I was just like having this brain fart. What on earth am I looking at here? We're going to have non-bonding orbitals here. The molecular orbital forms between the 1s orbital and one of the 2p orbitals, and so we go to get a sigma and a sigma star, And these are non-bonding, and they just sit there. So weird things happen when you get past just two of the same atoms in the second period. Use molecular orbital theory to determine the bond order of the FO minus ion. Is the ion paramagnetic or diamagnetic? So let's take a stab at this. Again, energy going up. Do fluorine over here. So fluorine has 2s and 2p orbitals, and oxygen, we're not going to worry about relative ordering of orbitals like we did with the HF or even with the NO. That's just too much. This is the oxygen. So FO minus, it's got an extra electron, right? Who do we think might have the extra electron, fluorine or oxygen? Who's more electronegative? Fluorine, right? So if we're going to choose where to put the extra electron, which would amount to a formal charge of -1, we're going to put it on the more electronegative one. So when I put electrons in here, oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. Fluorine has 7. 1, 2, 3, 4, 5, 6, 7. Oops, sorry, 7. And we need an extra electron. We're giving it to the fluorine. So then this is essentially an F minus ion. Then we're going to combine these. So we're going to get, from the S, we're going to get a sigma star 2s and a sigma 2s. From the p orbitals, so we've got fluorine and oxygen. We had to watch out for boron, carbon, and nitrogen. Be careful now. We don't have any of those, so we don't have to worry about this being a strange order of the molecular orbitals. The sigma will be lowest, and then the pi, and then the pi star, and then the sigma star. So this is sigma star, 2p, this is pi star, 2p, this is pi, 2p, and sigma, 2p. And, you know, they got a little higher. I'm not going to worry about it. So I've got 8 electrons here in 6. 8 and 6 is 14. So I'm going to put 14 electrons in here. So, you know, drawing all of this, that's all very weird, right? But once you've got these boxes, figuring out the number of electrons isn't hard. Fluorine has 7, oxygen has 6, that's 13. A -1 charge, we have to add 1, 14 electrons. And putting 14 electrons in these boxes is not hard either. It's the same rules, it's just the boxes are different. They look different. So we start at the bottom where the lower energy and count to 14. 1, 2, 3, 4, 5, 6, 7. Now, number 8's going to take his own orbital, right? And then they have to pair up 9, 10, 11, 12, 13, 14. The hard part is where those boxes came from, right? So now we want the bond order. Bond order is the number of electrons in bonding orbitals. So let's identify those. So this is a bonding orbital, and that's a bonding orbital, and this is bonding. So 2, 4, 6, 8 in the bonding orbitals. How is this not working? I'm trying to choose a different color for my highlighter, and I don't know what's going on. Oh, there we go. So antibonding would be this one and this one. Right, the ones with the stars. 2, 4, 6. So 8 minus 6 divided by 2. So that's 1. Okay? So, should this ion exist? Yeah, it's got a positive bond order. This bond should form. Is it paramagnetic or diamagnetic? It's diamagnetic. They're all 2 by 2. Everybody's paired up like the animals on Noah's Ark, right? So this is diamagnetic. I almost wrote paramagnetic. Those 2 words, good grief, they're hard to keep straight. Any questions? What about polyatomic molecules? More than 2. Yeah. So we're not going to get too crazy about this. So let's look at ozone. We've looked at ozone before. For the Lewis structure, we saw there was resonance, and so we had to draw 2 structures because neither one correctly describes what's going on. In valence bond model, we've got hybridization of sp2 on this oxygen, and it's overlapping and forming a sigma bond with this oxygen, and it's forming a sigma and a pi bond with this oxygen. And valence bond model is also giving us a double bond and a single bond for ozone. When in fact, ozone has 2 equivalent bonds. It doesn't have a double and a single. Molecular orbital theory can handle this. Molecular orbital theory says, well, these pi molecular orbitals are formed from 3 orbitals on each individual atoms, and they're delocalized over the entire molecule. And so, this is just showing the pi molecular orbitals, a representation, showing how those are delocalized over the whole molecule. And this is the real reason we need to talk about molecular orbital theory, because some of you will be going on to take organic chemistry. So this is the molecule benzene. It's C6H6, and it's got a ring of 6 carbons here. And so Lewis theory, we end up with a double bond and a single bond alternating, and we have a resonance structure where the double bonds are in different positions. The actual molecule has 6 identical bonds between the 6 carbon molecules. And Lewis theory and valence bond theory cannot model this for us, but molecular orbital theory can. So what's occurring here is that we've got delocalized orbitals above and below the planes of these carbons. Benzene is highly symmetrical, has identical bonds, it has a flat shape, and molecular orbital theory explains how this can be. So molecular orbital theory shows us that, unlike our simpler ways of understanding how bonds form, these bonds can basically be delocalized. They can be over the entire molecule. And that explains some of the things that we see experimentally. Any questions?